This video is on the binomial theorem and Pascal's triangle. We're going to use the binomial theorem and Pascal's triangle to expand any binomial to any power. Now we're not going to make those powers too high, but let's look at what happens when we take a general binomial, a plus b, two terms, and we raise it to a particular power. A plus b to the power of 0, like anything raised to the power of 0, is 1. And a plus b to the power of 1 is just a plus b. If I expand a plus b to the power of 2 using the box or the arrows like we just learned, you get a squared plus 2ab plus b squared. And the expansions of a plus b to the third, to the fourth, and to the fifth are shown here also. Now there's some patterns that emerge that I'd like you to notice so that we can reproduce them when necessary. The first thing is to look at the coefficients in each row here, and these are set up in sort of a triangular format on purpose. The coefficients are 1 and 1 for this one, 1, 2, 1 for the third row, 1, 3, 3, 1 for the fourth row, 1, 4, 6, 4, 1 for the fifth row. And so you'll notice that there's a definite pattern. There's symmetry here where it starts at 1 and ends at 1, but it also builds to some number in the middle and either repeats and then goes back down or just has a center term, a highest coefficient, and then goes back down using the same coefficients. The other thing to notice is that we have exactly one more term in the answer than the value of this exponent. Take a look. The exponent here, the power is 0. One more than that is 1, and there's one term in my solution. One more than this power is 2, and there's 2 terms in my solution. One more than 2 is 3, and there's 3 terms in my solution. So we can make a general rule about how many terms your answer will have by saying it's always one more than the power of the binomial. So if that's the case, a plus b to the power of 5 should have 6 terms in the answer. And of course we can count 1, 2, 3, 4, 5, 6. So a plus b to the power of 10 will have 11 terms in the answer. It's a good thing to know. You know how many spaces you're going to need to fill. Another pattern that I want you to notice is what happens to the powers of the a and the b in each successive term of the answer. Let's look, for instance, at a plus b to the power of 5. When you look at this one, you'll notice that we start with a to the 5th. That power is equal to the power I started with. And then look at the powers of a in each term following. I go a to the 4th, a to the 3rd, a squared, a to the 1st power. I don't usually write the 1. And really, this would be a to the 0. Remember, anything to the power of 0 is 1, which is why no a is showing here, because 1 times b to the 5th would just be b to the 5th. Now look at the b's. Notice the highest power of b is 5. It's at the end. And that's also the value of the exponent that you started with. And now, working backwards through the terms, the b's go down if you work backwards. So b to the 5th, b to the 4th, b to the 3rd. So we use the first term in the binomial to begin our variables, and we'll count down with our exponents. We'll use the second term in the binomial, the b, and we'll start with the highest power at the end of our solution and work our way backwards. So the b's will count down from the end, the a's will count down from the beginning. and we know that our coefficients will follow a pattern. In this way, we can fill in everything we need to complete our solution without having to do the arrows or the box a whole bunch of times to figure out what a plus b to the power of 5 is. Let's take a look at just the coefficients. So this expands this. It's called Pascal's triangle, and the only thing showing is the coefficients from what you had on the previous screen. I'd like you to notice that there are some patterns in the way that these numbers occur, because then you can reproduce Pascal's triangle at will anytime you need it. You might notice that it always starts with 1 along the edges, so that's important. The first row here, row 0, is 1, and the second one also has 1s. But now we put 1s on the edges. If you look at what happens when you add those, that's where the 2 comes from. And if you add this 1 and this 2, that's where this 3 comes from. And so if you add the 2 numbers above it, you'll find what to put in the next row below it. And so even if you go down here, I can look at 15 plus 6, and that's where this 21 comes from. And so once you begin this using 1s, then it's just a matter of adding and writing the answer and always filling in 1s along the edges. Try it on your own paper and verify that it comes out the same way. Let's look at an example, and this is one that you have on the other screen, but I'd like you to see how you can build the answer using Pascal's triangle. So since it's a plus b to the power of 5, and the first row is a power of 0, so the second row will be a power of 1 and a power of 2 and a power of 3, and notice it's this number here. So we're going to be looking at this row in Pascal's triangle to list out our coefficients. I also know that I'm going to have one more than 5 for the number of terms in my answer. So 1, 2, 3, 4, 5, 6 terms in my answer. These are the coefficients, 1, 5, 10, 10, 5, 1. So I can write those in right now. So let's see what else we know. We know that the first term in the binomial starts with a power that's here already, 5. So I'm going to put a to the 5th in my first slot. I also know that those count down, so I'll have a to the 4th in the next slot, and a to the 3rd, and a squared, and then no, a to the 0. My b's, the second term in my binomial, are going to start at the end with the power of 5. So that's going to be here. And those will count down backwards. So b to the 4th there, b to the 3rd here, b squared, b, and then nothing. Now, since this is all positive, I'm just going to put pluses between all of these, and I'm done. I have expanded a plus b to the power of 5. And if I had bothered to do all the work with the arrows or the box or however you did it, taking 2 at a time and getting an answer and multiplying them together, I would get exactly this solution. So it's a very helpful shortcut. Let's look at one that has something other than a and b in the section, in the slots there for the binomial. So since I'm looking at x minus 3 to the power of 7, I need to use this, right here, this row in Pascal's triangle. So I know I'm going to have one more than this for the number of terms in my answer. So I'm going to have 8 terms in my answer. I'm going to make this smaller because I'm going to need quite a bit of room here. And we're going to go ahead and make 8 slots. On your own page, you're going to want plenty of room. Our coefficients are going to be 1, 7, 21, 35, another 35, and we're working backwards. Remember, this is symmetric, 21, 7, and 1. This is coming right from the row in Pascal's triangle. Once we do that, we're going to need to fill in our A's and B's, except that this doesn't use A and B. So what's in place of the A in this example, in this problem? In this case, A is our X. What about B? Be careful. B isn't just 3. B is negative 3. And it's going to be very important that we don't lose that negative. So let's take a look at filling in our A's, in this case, X. What's the first power of X going to be? I hope you said 7, and that's going to go here, and then we're going to count down. X to the 6th, X to the 5th, X to the 4th, to the 3rd, X squared, X, and then there's no X in the last one. Now, here's where it can get a little tricky. We have a negative 3 that is also going to get raised to the 7th power, and it's going to go here at the end. So I have a negative 3 in parentheses to the power of 7. Those parentheses are vital. You're going to be doing these in your calculator, and it's important that you type the parentheses or your calculator will not always give you the correct answer. We'll talk more about that in class, but I want you to think about why. So if we're starting at the end with negative 3 to the power of 7, we'll work our way down to the power of 6, to the power of 5, 4, 3, 2, 1, and nothing. To complete this, you have to be careful to follow order of operations, and you need to use your calculator to help you fill in the numbers. So each term, each slot needs to get multiplied. Make sure that you follow PEMDAS, order of operations, and that you do the parentheses and the exponents first, and then you'll get a number, take it, multiply it to the coefficient. I'd like you to try to finish cleaning up this problem here, and then we'll check it in class together. If you're an honors student, I would also like you to try this problem to prepare for class. In summary, we can recreate Pascal's triangle starting with 1s in row 0 and row 1, and then putting sums below each pair of numbers. Pascal's triangle helps us quickly expand binomials raised to any power. It's important to define A and B carefully, follow order of operations, and pay attention to the details.